Hello, my name is Kareem Shehata. I'm one of the authors of Epione, a lightweight contact tracing system that provides strong privacy guarantees. In this talk, I'm going to cover the basics of contact tracing and how digital contact tracing apps work, some of the privacy pitfalls therein, and how we solve some of these problems with Epione. So let's start with contact tracing. First, what is contact tracing? Contact tracing is the act of finding all the people that you have been in contact with over some defined period of time, and we define contact as being within a certain distance for a certain period of time. So for example, with COVID-19, that would be over a 14-day window, anybody that you've been within, say, 2 meters of for 15 minutes or more. So if we're looking at an example of this population of people, we want to do contact tracing of the person in green as they went through their daily life, and that would be all these people in red. An important caveat, we're not looking at any indirect contacts, which is another topic for another time. So how does this work with Bluetooth? So let's say Alice and Bob are in close proximity. They both have their phones, and their phones have Bluetooth or some other short-range radio network. They use that network to exchange tokens. What are these tokens? These tokens are values that appear random, but can be used afterwards to figure out who was in contact with whom, and how you set up these tokens sets up different values for different impacts to privacy. So let's say Alice sends TA to Bob and Bob sends TB to Alice. They both record these tokens in lists on their phone. So Alice records that she received TB and sent TA, and Bob does vice versa. Now let's say sometime later, Bob goes to a hospital or clinic and is diagnosed positive with whatever disease we're considering, in this case, say COVID-19. He will take his list of sent tokens, all the tokens that Bob sent, he's going to upload to some central server or public notice board. Alice can later query that public notice board and see, okay, what are the tokens sent by users that have been diagnosed positive, and she'll compare that to her own received tokens list to see if there are any matches. If there is a match, she gets an alert on her phone saying, hey, you've been exposed to the virus, you need to be tested. So there's some obvious privacy concerns here. Can these apps be used for location tracing or user tracking without location, but just like where they've been over time? And so there's some obvious privacy concerns here. Can these apps be used to track location? If we just do a naive location-based approach, could that lead to revealing somebody's location history? Can this be used to track somebody's movements over time? Can this be used to find out someone's social graph, so all the people that you have been in contact with, or even a pseudonymous graph, as in given a set of identifiers, who's in contact with whom? Also, we could expose the infection status of somebody. Are you able to tell who was it that was exposed to the virus, or who brought your exposure out? Somebody could make false claims, claiming to either falsely have the diagnosis or falsely be in contact with somebody. And an important differentiation is a health authority versus other people. So that central server, if it's operated by, say, a health authority, what do they have access to versus some other third party? That's an important dimension for privacy. So a few things we're not going to tackle here. We're not going to look at indirect contacts, as I said, and we're not going to look at testing, isolation, enforcement. We're also not going to look at philosophical questions like what information should be available to whom. We're going to say that the end user wants privacy, and we're going to try and enable that to happen. Whether or not that should be the case, we're going to leave as another time. And that's important because this has actually been raised right here in Singapore, that Singapore started this whole contact tracing with applications idea with Trace Together, which is a very cool app, but it puts a lot of trust in a central authority. And This is at odds with some of the privacy concerns of saying we don't want to expose someone's social graph and who's been in contact with whom, but that means that the Ministry of Health can't do direct follow-ups. These are at odds. And whether or not that is a good or a bad thing is a philosophical question. We're not going to address that here. We're going to say that if this privacy is desired, here's how we can solve it, and leave the philosophical question to another time. So let's dig into Epione and how Epione works. With Epione, we propose to use private set intersection cardinality to solve a lot of the privacy issues of the baseline systems that use this approach. So private set intersection allows, let's say, two parties to compare their sets and reveal only the values in common to one party. And private set intersection cardinality does the same thing, but reveals the count of the items that are in common to one party. So neither set is revealed to the other side, only the count is revealed. So how does this work? Let's first go into, we need a prerequisite, which is we need some transform that is commutative and reversible. Usually this is elliptic curve computations. Consider it like a deterministic encryption that is, again, commutative. It's not actually an encryption, but you get the idea. So how do we actually do this? Let's say the client, a phone in this case, has set Y and the server has set X. The client is going to take its set Y and it's going to transform it by some random value R and send that to the server. So the server gets these randomly transformed values that it is not able to map back. The server then takes that, transforms it itself by its random key K, and shuffles the order. So now the client gets this back, this set W prime that is in shuffled order and transformed by value K. So it can't tell which token maps to which in the input set, just that every item has been transformed by K. The client then undoes the transformation by R and gets out of it basically the set Y transformed by the server's value K, but the client doesn't know what K is, only that every item has been transformed by K. Notice that the server doesn't learn what the set Y is either. The server does the same transform with K on its set X and sends that over to the client as well. Now the client has two sets. It has V, which is Y transformed by K for each item, and U, which is X transformed by K. And it's a simple matter of going through every item in the two sets and just looking for any items that are in common. And let's say that U1 is equal to V2, and it's able to say, oh, hey, we have an item in common, therefore that is an item in common in the original two sets. So the client can't tell what the items are, only that what the count is, or the cardinality of the set intersection. So this is great, and it allows us to do private set intersection cardinality, but there's a couple of problems. The first is we have to compute over the entire set, but also we have to send all the values over the network. Well, with contact tracing, the client has a small set, but the server set could be very large, and sending that entire set over the network is prohibitive or impossible. So how can we solve that? We could use a Bloom filter. It's more compact, but still order n, so that means it's going to grow with the size of the server set. It also has a false positive rate. We could try sharding the values so that you have them within a geographic region, for example, or dates and so on, but that leaks data, and so we're losing our privacy guarantees. And that's also very problematic for dense areas, for example, in Singapore. We propose a different solution. We propose to use private information retrieval. Private information retrieval is a very cool technique where we use homomorphic encryption to send a query from a client to a database server. The database server processes it and sends a response back, but the server is not able to tell what the query was, or what the result was. By using homomorphic encryption, the server does all the processing, the client gets a result, but nothing is revealed to the server. So how do we use this with PSI-CA? Well, we do the first transform the same way. So we're going to transform all of the client tokens by the server's value k without the server learning what any of the values are. Then we treat the server's database U as sort of a lookup. So the client takes each of their tokens and just does queries against the server to see, are these values of V in U? But the server doesn't learn what V is. So the server is not able to tell what any of the client set is anymore. So this has all the advantages of PSI with no false positives and requires a lot less bandwidth than Bloom filters. Now, if we compare this approach to a lot of the existing approaches out there, so Google and Apple's system is fairly famous. It's a very similar system to DP3T and PrivateKit, etc. This provides protection from a lot of the server-side privacy attacks, but not from a lot of user-side things in terms of infection status and so on. They protect those by wrapping it in an API, but there's still the potential for leakage there. And it does provide social graph protection, and it depends on how it's implemented for false claims. We, by contrast, provide protections against each of these, and that's the advantages of Trace Together, which has does not protect against the server, but protects against user attacks, unlike the Apple-Google attack setup. And finally, just to mention that there is a setup by Covey Canada, which is a very cool setup, and provides some very extensive functionality, but requires a lot more infrastructure. It requires 3 independently operated server sets. So we don't require that. We require just 1 server or 2 if the healthcare provider is providing a separate testing facility. So in summary, we can extend the Google Apple model to provide better privacy protection by using PSI-CA, and we use PIR to scale this up. We're currently working on an implementation with OpenMind and the Ito teams, and we're looking forward to any possible collaborations. So if you see any opportunities there, please feel free to contact me. I would love to talk about any collaborations. Thank you very much. Take care and stay safe.